Oh my.
We're just waiting for any participants to enter.
Okay.
So this was on a very like short notice. Like we started putting about your webinar, like any information about your webinar out on just yesterday. So we're so this was on a very short notice, but yeah.
Oh, I understand. There are some times where I will do a webinar that that has, you know, one or two, or even just a recording for future broadcast, and other times there will be many more on there. So
Yeah,
that is
which is
exactly
completely fine. Which is, ultimately we're having it in record, so it's accessible to the people that it needs to be accessed by. So that's great.
wonderful.
Yeah.
Thank you. So do you work at with Ritash at the Fossil Museum or
Yes.
in general? Yes, that's
So
wonderful.
I'm the creative director and curator at
Oh,
Tethys
wow.
Museum. So yeah.
Lovely. I hope that I'm able to visit someday.
We would love to have you there. We will be in conversation with you regarding that very soon. So
Okay.
yes.
Wonderful.
So we have a we have a section on dedicated to energy and geothermal development in India, which has been taking place so long since ages. So we have a section
Wow.
there about the geothermal also.
Wonderful. Oh my
From the
goodness.
Himalayas, but we are concentrating more on Himalayas. So all the things which are happening in Himalayas and how we are trying little bits about doing some projects in geothermal in Himalayas, that is what we are highlighting there.
Wonderful. Oh my goodness. It sounds wonderful. I didn't take the time to look at what city you're in over there.
We are in Kasoli.
Okay.
This is just between very near to Chandigarh. You have heard about Chandigarh?
Got it.
Chandigarh and Shimla, it's sandwiched between Shimla and Chandigarh. It was
Good. Good to know. We have a few projects that may be going on there with one of our KSA, Kingdom of Saudi Arabia clients, has a couple of projects that may be coming together in your area. And that's all I know about it right now. I work with them as the developers over there, so to speak. So whenever you do have a large project or a project you'd like to develop, we have some people who work over there in developing projects. They're pretty good at it too.
Wonderful. That's so wonderful. Should we start regardless? I mean,
I think we'll be doing a live streaming of this on YouTube in near future also.
Yeah.
So at that time we will invite you to just answer some questions and answers.
Good.
At that time. Huh?
Maybe I love that.
Yeah.
Send me some links to that and I'll share it around also. And you're right, it was very quickly put together, but I had this opening on a very busy Monday and I said, I said, it really needs to be done. This is a whole new market, a whole other market that needs this, and especially the importance of this time. So I am excited to see it and share it around once it's done.
Yes, definitely. Because I think India is a very potential market for geothermal in near future. Yeah.
It is for sure.
Yeah.
All right.
So, okay.
Shall we start?
Yeah.
Okay. I'm gonna start sharing my screen. Good evening. I'm Oshin and I welcome all who are present here for this webinar on National Science Day, organized by Tethys Fossil Museum on geothermal systems with a focus on thermal energy networks by expert consultant J. Egg. After serving in the US Navy nuclear power field, J. Egg began a career in mechanical design engineering and AMP contracting. Now, as an expert consultant, Jay sits on several technical code committees internationally, notably the Technical Committee for IAPMO, Uniform Mechanical Code. Jay has co-authored 2 McGraw-Hill textbooks focused on geothermal HVAC technologies and continues to write curriculum and host lectures on the merits of clean heating and cooling technologies. Jay Egg is president of Egg Geo, which provides expertise in education and engineering and defining the future of geothermal globally. And now I will give a little brief on Tethys Fossil Museum. The museum is built from 20 million year rocks of Kasoli sandstone, beautifully chiseled to give the museum an aesthetic look. This webinar on National Science Day is organized by members of Tethys Fossil Museum and Research Center, supported by Indian Geoparks.in and Agni Yodgara Lava Energy. Before starting today's deliberation, I will brief anyone present here about Tethys Fossil Museum and Research Center, which is coming up in Kasoli, Himalayas. The museum is well connected with the Chandigarh International Airport via road and railways built 100 years ago and is a UNESCO heritage site. Geologically, the museum is located on debris concealing the Dakshai-Subatu boundary, which signifies the closure of Tethys Sea and the evolution of terrestrial ecosystem. Water that we drink in the museum is from a bore well drilled into 40 million year old white quartzite sandstone, which is a marker bed extending from Pakistan to Burma in the east. Tethys Fossil Museum, as the name suggests, houses fossils collected from different parts of the Tethy Himalayas. The proposed theme of the museum is evolution and extinction and journey from fossils to fuel. The museum will be a repository of various scientific evidences, vividly bringing the Tethys back to life by displaying collected fossils and rock specimens. It will not only cater to the layman, but it's likely to enthuse geologists and promote HC exploration in the Himalayan region, signifying the gradual evolution of life on this planet and the development of the mighty Himalayas. All these fossils are a part of the museum repository. We have 2 sections in the museum. First section is about natural evolution, and the second section is about man and his environment, in which we have an energy section, where we discuss future challenges faced by mankind. Present here with us is also Dr. Ritesh Arya, founder of Tethys Fossil Museum and Agni Yodgara Lava Energy, bringing right to free, safe, sustainable water and energy for all. He is a geologist known for finding water sources at multiple locations in high altitude, cold and mountainous desert of Ladakh, including the Siachen Glacier, which made him a Guinness World Record holder. In 2014, he was appointed as the director of Water and Geothermal Section at the International Sustainable Energy Organization in Geneva. He has a specialization in Himalayan geology and hydrology and is passionate about exploration of fossils, groundwater, geothermal, and understanding of tectonics and climate change, and is currently making a museum of evolution in Kasoli, Himachal Pradesh. For the last 30 years, he has been collecting fossils from Himachal Pradesh and Ladakh. I would now request Dr. Ritesh Arya to take over and commence the session.
Thank you, Oshin. Good morning, Jay. Again.
Good morning.
So before I give it to you, I'll just tell the importance of this day and why we are celebrating it. So today we have National Science Day. I'm not able to share it.
I just stopped sharing, so you can now.
Okay.
Yeah.
And I'll be just telling briefly about today's. Can you see the screen now?
Not yet. You can. I just did like an option of sharing, allowing sharing screen, so you can now access it, I'm guessing.
There
Yeah,
you
okay.
go.
Yeah. So today, the theme of the today's National Science Day in India is integrated approach in science and technology for sustainable development. And why we are celebrating on 28th April is 20th February, because the Raman effect, the famous Raman effect for scattering of light, was discovered by Professor C.V. Raman on this day. And he was awarded Nobel Prize for the Raman effect for understanding the atomic role in scattering of light. And his instruments, now we are talking about science and technology, he had the concepts, and the instrument which he used was a prism at that time. And when he was appointed the Fellow Royal Society, and he was asked what is the achievement he has done, next achievement, he said that he's going to win Nobel Prize in another 5 years. So he was so confident about his research and science and the concepts, with little resources, with little technological development, but the concepts, with the prism, he was able to do all his experiments. And in 1930, he really won the Nobel Prize. So that was his conviction for science and making the instrument. And then after receiving this award, he was asked, well, he just referred, when I got my Nobel Prize, I had spent hardly 20 rupees to make my equipment. 200 rupees to make my equipment. And that is about, now today's terms, it's about $3.
Wow.
$3, and he got this Nobel Prize. And the spectrograph he made for detecting and measuring electromagnetic waves was made for this. So, and then somebody asked him about the religion, and he just gave it a very, very simple reply. And then, if there is a God, we must look for him in the universe. If he is not there, he's not worth looking for. The growing discoveries in science of astronomy and physics seem to be further revelations of God. So that was his connection with the universe, with God and the religion, and the way he just lived his life scientifically. So this was quite inspiring. And then the government chose this day to celebrate as the Science Day. And then when we were thinking about who we should be now inviting, so I had been listening to you, Jay, and I think no better person than you for the would have been now. Now we are just going into another venture from astronomy in beyond space and now below the earth, below the surface of the earth. So we will be just hearing about you. But before I just give the stage to you, I'll just talk briefly about the geothermal potential in India and what has been done in India, and how we plan to go in near future. So we had developed this concept of Agne Yodgara Urja in 2010, when we did a project with India, Iceland, Norway, and they were trying to do something in geothermal exploration as a joint venture in Himalayas to work for communities living in remote areas, and how we can help them, in solving their energy problems. And then this is basically Agni Yodgara means lava energy in Sanskrit, in our traditional language. So, and when we were going back in time and we were exploring different sites in Himalayas, this is one of the sites in Manikaran in Himachal Pradesh. This is a geothermal site developed 500 years ago. And this is a Sikh Gurudwara, a temple. And free food given by devotees from the money, and cooked in free energy, that is geothermal energy, is cooking the food, and it is served free of cost since 500 years ago. So this is the first geothermal utilization project, I think, in the world, which is continuing till now. So that is the beauty of the geothermal energy utilization in India, and that is a practical example. Now they have developed a swimming pool. Whatever, even if tea you have get there is of geothermal. So inspired by this traditional wisdom in Manikaran, I developed this concept of Agni Yodgara and felt that it is right to free, safe, sustainable water energy for all. And geothermal can actually pave the way for this development in near future, because this is once investment done, it is energy for free energy for all, and that has been documented in the Manikaran village in Himachal Pradesh in India for the last 500 years ago. And this is just the team, from Iceland, Norway, and we were doing a project in Ladakh, Uga. We did some university campus, you can say discourses, webinars, not webinars. At that time, it was seminars. So we just interacted with seminars. Now it's webinars. And then I developed this we developed this different sites in Himalayas, in Indian, northwestern Indian Himalayas. These are the different geothermal sites and the mechanism. And then the Agni Yodgara site is basically vertical tunneling, huge tunnels built vertically. And then we all the sewerage water we get, we dump it there, and then the heated water comes back, and then we were just developing sewerage and a system like this for a big cities like Delhi, Bombay, Hyderabad, Madras, where sewerage is also water problem, but geothermal can really play wonders. So this is one of the sites in the Himalayas. This was done an experiment by DRDO, and this is just a geyser oozing out from a borewell drilled in Chumathang. And so there is potential at, we have got temperatures of about 88 degrees, 90 degrees, 84 degrees, that is almost like, and 120 degrees also it has been reported,
Wow.
So very, very interesting things happening here in Himalayas. And then this is like a border between glaciers, Siachen Glacier. So it is between Pakistan and India. Now it has been open to Indian public, but here we see again a shallow well, warm water. We drilled a well. We got not only potable drinking water, but lukewarm water. But here the energy cost is like transporting all the fossil fuel from it comes from maybe the coast of Gujarat, and then traveling thousands of kilometers and going to this place. But if we can develop this geothermal resources there and use it for maybe heating, water, space heating, agriculture. So there are a number of applications which can be used, which really can change the entire energy scenario there and make the life of people and the shepherds and the nomads and the people living in that remote regions very comfortable. So this is like the various utilizations of geothermal resources, how we can use it. And this can be done in a very effective way, we don't require much technology for this, but a very simplistic way. And this is an example from Kenya. They have done it in a very, very effective way, 78 degrees temperature. This is what the temperatures which you get in the Himalayas. And then just use it for heating water, pasteurization of milk, fish farming, greening, increasing the greenhouse vegetables effect. And then now I always use your slides, and these are just very, very futuristic slides, I must say. And maybe in one day, everybody understands this phenomena and make it mandatory to put ground source heat pumps for cooling, because India is it is estimated then in about as the per capita income increases, then we have a lot of air conditioning to be done, but that will impact the pollution levels, or the greenhouse gases increase. But if we can use this, I have this, this is again designed by you. So I find it like anything planning, it has to incorporate geothermal energy, into it. Otherwise, it is no planning now. And how we can popularize it in India, because India requires it, growing infrastructure, growing energy demands. And if we cannot actually put these things right here, then we will become an energy starved nation in near future. So if geothermal energy can be incorporated, and this is self-explanatory diagram for any policymaker or the politicians to understand what geothermal can actually do for the Indian economy and the buildings in near future. So, and this is an experiment by Gibbs. They did this is the place where I live, Indian Institute of Science, ISB, business schools. So they have done this geothermal heating systems and tried to replace this cooling system, the coolers, water coolers.
Amazing.
So we have made some efforts, and India, lot of a friend of mine, Arjit, he's also doing good work, and recently he did a building in Roorkee, where he did cooling with the hybrid solar installed and ground source heat pumps, and that was a very successful venture by him. So little bits are being done, but it has to be done on a very mega scale, like then it will be very good. And now, not taking much time, we would like to learn much more from JEG and how India can benefit from this mega ventures in geothermal, and how futuristic cities can be architecturally, not only architecturally, but how energy efficient geothermal can make them, and make, because we require cooling in the heating in the Himalayas and cooling in the entire Indian plain. So both applications of cooling and heating of geothermal is applicable here in India, and we have a major portion of it for cooling right from Chandigarh, where we are holding this webinar, and right to South India at the tip of it. So everything we require cooling, and from here when the Himalayas start, and we require heating in winters. So that makes it a perfect hub for installation in near future. So I now invite JEG to deliver his talk on geothermal systems with a focus on thermal energy networks. And we are excited to hear about you, from you.
Thank you. Ritesh, thank you so much. I'm going to share my screen. I'm so grateful that you took the time to share a little bit about your work, because I have been very interested in understanding better what you do, and this has been very helpful for me to do that. So everybody can see my screen now, I imagine, and I appreciate, I consider it the greatest compliment when people use, as you do, some of the images and slides that we've developed over the years, because they are for the public to share and get the information out about geothermal heating and cooling systems. And I love, Ritesh, that you talked about the water and energy for all, because it really is about water and energy. When we're looking at a geothermal opportunity in a city center, and we'll start with this slide that you had up earlier, there is the opportunity to tie in wastewater energy, infrastructure exchange, such as from subways, and such as from surface water and other things going on underground, to use that energy and move it around a city that has heating and cooling needs. And we're going to talk about how that's done. In many cities and communities throughout the world, there are both needs for heating and needs for cooling. And we find that a lot of our big cities need a lot of cooling, and they're what we call cooling dominant, meaning they have waste heat. And if you think about data centers and so forth, they have waste heat. And when you look at all that waste heat and you consider that much of the world needs heating, just like Ritesh shared earlier, that heat, instead of going out the top of the buildings through cooling towers and air-cooled equipment, can be piped into what we call a thermal energy network. And that's what we're going to get to as we talk about these types of systems. So as I begin to share this, I imagine the time allotted will take us for about another 32 or so minutes to the top of the hour. Is that correct, Shaheen and Ritash? Oshin and Ritash?
Yes, correct. Jay.
Okay, that's perfect. I will time it accordingly. It's the perfect length for what I would like to share. As you look at the learning, we consider the learning objectives. What I'd like for people to notice is that as we go through this, I just want everybody to understand that there are certain context and verbiage we use in geothermal, and understand how important it is to share this with other people. So I'm so grateful that this is being recorded and will be put available on YouTube. This technology is not only important to energy and CO2 reduction, but it's important to health and human safety and imperative to our industry goals. So as we understand the barriers to this, we'll be able to understand how we can, everybody attending today can use our abilities to share this information and make these changes to our city centers, to our communities. And you can hopefully leave here with the intent to share this and help people understand how important it is. So we're going to talk a little bit about city-based hydronic infrastructure, a little bit about some advanced ideas with regard to community thermal energy networks and what's next for the world for thermal energy future. As we go into this, most people have a very simplistic view of what the challenges are that face our world with regard to CO2 emissions and greenhouse gas emissions. And that's why what we're doing here is so important. And this political cartoon kind of shares a little bit about that. If you look at this, you can see that people say they're saving the planet with electric vehicles. Others say they are into green hydrogen. Others have battery technologies, and others talk about PV, photovoltaic. Meanwhile, about 40% of our energy budget has to do with heating, and the other side of that, cooling. So in order to comply, if we're all driving electric vehicles and using wind power and solar power, we still haven't approached 40% of the energy concerns and the related emissions, and that is for building heating, which is 40% of our greenhouse gas emissions. The way we attack or approach the challenge of building heating is using one of the most fundamental yet brilliant technologies available, and that is the heat pump. In other words, just like a refrigerator, we use heat pumps, and a refrigerator is a heat pump to heat and cool our home. So you can see, just like this refrigerator uses the Carno refrigeration cycle, that's the compression cycle to pump heat out of the refrigerator. A home uses that same technology, heat pump technology, to pump heat out of the home or building and also pump heat into the home or building. So that Carno refrigeration cycle uses a compressor, which is indicated here in this geothermal image. It uses a condenser, which is the heating coil and expansion valve, and an evaporator, which is the coil which rejects heat, which absorbs heat from the outside underground. An air source heat pump also is a renewable energy product. It's just that the geothermal portion, or the geothermal exchange, provides greater energy capacity and a better solution overall, especially as we look at our city centers. So in this image to the right, and I will send this out to Ritesh and Oshin afterwards, but it has, and I'm not going to show it right now, but it shows how the Carno refrigeration cycle works if you click this hyperlink. And if we had a longer presentation,
No, yes, you
sometimes-
can increase the time, Jay. We don't have
Okay.
limitation of time.
Okay, well, I will.
You take your
I'm
time,
going-
just make it a wonderful video so that every, well, you can say, if you're just making it for a positive policy matter, you know. So you
Okay,
like to
I'm going
spend
to take the time then. Thank you, Ritesh. I'm
any
going to
amount of time. Time is no limit.
Okay, thank you. I will use the time that's appropriate then. Thank you, sir.
Thank you very
Appreciate
much.
it.
Thank you.
Well, then we're going to click this because one of the things I find in my teaching, I have the privilege of teaching the U.S. Department of Energy, the new engineers that are coming there to work in the Energy Information Agency each year. And one of the things that's most difficult to understand is this, and we're going to click it right now, this Carno refrigeration cycle. So I want to show for everybody listening, because it may be the only time you've ever had the opportunity to look at it. In the Carno refrigeration cycle, which this is exactly like a refrigerator operates, you have a compressor, you have a condenser, you have an expansion valve, and you have an evaporator. And using this in the summertime when it's hot outside, the compressor creates hot gas. It's just a compressor like an air compressor, but it's using a closed refrigerant system, and it compresses hot gas, then it runs it into a condenser, which is what is considered the heating coil of the refrigeration system. And that condenser condenses refrigerant, and as it does it, it creates a heating effect. After it goes through the condenser, you have a high pressure liquid that goes through an expansion valve, which drastically drops the pressure and begins the evaporation process of the refrigerant. In the evaporation process, just as a human being sweats and on their hands, that sweat gives a cooling effect as it evaporates, that's the same thing that happens in a refrigeration system. As the refrigerant begins to evaporate, we get a cooling effect, and the evaporator absorbs tremendous amounts of heat while it's cooling, and that evaporation of that refrigerant then leaves a cool, low temperature gas that returns to the compressor, and it is compressed and becomes a high temperature, high pressure gas ready for condensation again. So as you look at the summer or cooling effect, you'll see that this has, for air conditioning and heating, it has a special component called a four-way valve, which allows the heat pump to switch. And you're watching it right now. Look at it switch from summer cooling to winter heating. Now it's cold outside. What did it do? It switched the condenser from the outside to the inside. Remember, I said the condenser coil is the coil that gives off heat. So now it can heat indoors. And that's how it operates. And that's the beauty of a heat pump piece of equipment in providing heating and cooling. It is not a heat burning device. It doesn't burn electricity to make heat. Rather, it uses electricity to run a pump, this compressor, which pumps heat. And now it's switching from winter to summer again. You can see that, to create, to move heat from outdoor to indoor and from indoor to outdoor. And that is what's happening right here. So this heat pump device, which is indicated here, uses energy from underground, compresses and intensifies it, and it can be used for radiant floors, for radiators, for water heating, for pool heating, and it can use very low intensity heat easily as low as 5 degrees Celsius. If you have 5 degrees Celsius underground, it can create all the heat you need for domestic hot water, for heating, and for cooling. So when you put it into a home or a business, this heat pump can use a distribution ductwork to pump heated and cooled air into your space. As we said, it can use radiant in-floor conductors, hydronic loops in the floor to heat the space. You can use radiators, you can use domestic hot water tanks, and all types of distribution equipment to provide this heating and cooling. Once again, whether you're using an air source heat pump or a ground source heat pump, they are both renewable energy heat pumps, because when you consider this, we're not burning fossil fuels to create heat. As you see in this air source heat pump, it's absorbing heat from the outdoor air, which can be very cold, but a heat pump can still extract heat from that cold air outside. The difference is when you use a geothermal heat pump, the ground underneath our feet is always going to have more heat available in the winter, and it's going to be cooler in the summertime. So where outdoor air temperatures fluctuate greatly from summer to winter, as we all know, underneath, when you get below a couple of meters underground, the temperature is going to be pretty much stable year round. And that's why we talk a lot about using the underground as a heat source and heat sink and moving the heat around. We'll talk a little bit more about moving the heat around. First of all, it's important to understand how we rate the performance of heating and cooling equipment. If air conditioning and heating equipment is rated in energy efficiency ratings or more on a worldwide basis in COP, which stands for coefficient of performance. And so coefficient of performance is the one I usually focus on, because EER is more of a cooling efficiency rating, and it's more a US based rating. The world normally uses COP because it's a very simple equation. Coefficient of performance is the BTUs delivered divided by the BTUs consumed, a very simple ratio. So if you deliver 36,000 BTUs and you consume 12,000 BTUs of energy, then that means you have a COP of 3, or meaning the heat pump is 300% efficient. It's delivering 3 times the energy it's consuming. The BTU rating, for those that haven't studied thermodynamics, is very simple. One wooden matchstick burned from the top to the bottom is 1 BTU of energy, or 1 British thermal unit. 1 British thermal unit is the same amount of energy it takes to raise 16 ounces of water 1 degree Fahrenheit. So to correlate that to something we use more commonly in the world, a watt of electricity is equal to 3.412 BTUs. So a watt of energy is now equal, we know, to about 3.5 matches burned. So 1 watt of energy, if you put 1 watt of energy into a 16-ounce bottle of water, it will raise that bottle of water 3.4 degrees Fahrenheit, which is you can easily correlate that to Celsius. The other way to look at this is if you use 1 kilowatt of electricity and an electric heater like you see here, it will deliver, 1 kilowatt will deliver 3,412 BTUs per hour of heat. That's just very simple equations, because we just talked about that in the last slide. However, if you use a heat pump, that 1 kilowatt of electricity will deliver 17,060 BTUs of heat, especially with a geothermal heat pump rated at a coefficient of performance of 5. And you can see in this image very simply how that's done. A geothermal heat pump using 1 kilowatt of electricity will be able to pump another 4 kilowatts of heat out of the ground because it's a heat pump and delivering a grand total of 5 kilowatts of energy. So this is such an important part to understand in the geothermal, in the heat pump realm. Now these heat pumps, and you can see the two different types here, air source on the right, on your right, and geothermal on the left. It's pretty simple. You either use an air source heat pump or a geothermal heat pump. They're both the same technology. However, with a geothermal heat pump, the outside portion is underground, right? Because it's transferring energy with the underground temperature rather than the outside air. So these are unitary heat pumps usually, and these are split systems usually. There's an outside condenser. So in this unit that you see on the left, it has the complete heat pump, including the compressor, evaporator, condenser, and expansion valve, all in one unit, where this one has two parts because it's transferring heat with the outdoor. The way that geothermal heat pumps can help buildings heat and cool has to do with how many hundreds of different types of heat pumps you can put into a building, whether it's a school, a university, a hospital, a hotel, or a single family home. You can choose this residential grade piece of equipment like Carrier makes, as well as all the other manufacturers here on the left. You can choose a hotel type stackable geothermal heat pump like you see here, which you might see in a Marriott or another regular hotel. This is what's called a modular heat pump, like you might see more commonly in hotels and apartments. And this is a geothermal modular unit, which these are also made in air source as well as geothermal heat pumps. You can use a horizontal heat pump that's put between floors or above the ceilings in an office or a home like you see here. And interesting to note, you can see the geothermal pipes tying into the heat pump, tied to the little fluid circulators that pump the fluid, the water, into the heat pump to provide the heat source and heat sink. Here you see a bigger commercial heat pump that provides the heating and cooling for maybe an auditorium or a cafeteria or a restaurant. And here's a more singular common area heat pump here. The common thing you see with each of these is they have fluid pipes that are filled with water-based fluid that provide the heating source and sink for these heat pumps. To get a closer look at some of the different types, water to air heat pumps look like this, meaning they use water source, but they distribute air through ductwork. And you can see that this is another water to air heat pump above the ceiling. And these are also water to air heat pumps, the modular ones like you might see in hotels and apartments, and the vertical stack units like you might see in hotels. Then we get into another type of heat pump that's still geothermal, which is water to water, as it says here. That might include this, which is a domestic hot water dedicated heat pump that makes all the hot water for a building, or a pool heat pump like you see here, which provides all of the heating you might need for a pool in a resort or a home. On top of buildings, you can also replace existing rooftop package air conditioners with geothermal heat pumps, which will pop right onto a roof curb on top of a commercial office building or a shopping center. These are getting a little bit more into the details. These are dedicated outdoor air units that are also made in geothermal configurations. So those are just a few of the basic types of heat pumps that use the earth underneath us to transfer to as the heat source and heat sink to create a thermal energy network. Now, when you look at this is what I promised to get into a little bit. The in a community or a thermal energy network, you have cooling dominant equipment. Even on the coldest day of the year in a cold climate, you'll find that your commercial office buildings and your factories are cooling dominant, meaning they need cooling to help them to do their processes. So when a building needs cooling, it's rejecting heat. And you can see down in here, these little arrows show that these buildings are cooling dominant, so they're getting rid of heat. And they put it in, when they do that, they put it in rather than to cooling towers in a perfectly matched or a good thermal energy network community, they reject that heat into the pipeline for that city, which is the thermal energy network. And then your homes and apartments and buildings that need heat can use that heat rather than it being wasted. And with these types of systems, the beautiful thing is there's no more outdoor equipment to replace or to see or to have to service. They are more hurricane and storm resistant because there's nothing outside that can be hurt by the elements and blown away. They have a longer lifespan because there's nothing outside to weather. They eliminate the combustion component that is normally needed with boilers and furnaces. They eliminate cooling towers, which are normally needed to exhaust heat from buildings. They have noticeably superior comfort in both the heating and cooling modes, and there is remarkable system efficiency at standard equipment pricing. These heat pumps we're talking about here don't cost any more typically than a standard air source heat pump. They simply require this infrastructure to be put in first. Just like in a city where you need water pipes put in so that you have city water and city sewer put in and central electric, this is something that the world is adding currently, these thermal energy networks, to make this part of our design infrastructure. As we do this, we are creating cities that will be able to provide that 40% of our heating and cooling budget simply by the installation of these pipes and stubbing them into buildings that we currently have. So not only can we do this in new cities, but these are currently being retrofitted into existing cities and communities. The reason this is so important, is because as we convert from combustion heating to electric heating and cooling, we find that electric heat pumps that are air source require a lot more peak energy consumption in the wintertime than geothermal heat pumps. In the ASHRAE headquarters, which is the American Society of Heating, Refrigeration, and Air Conditioning Engineers, which is actually a worldwide society, as I'm sure everybody listening to this realizes, they installed air source heat pumps in their headquarters in Atlanta, Georgia, US, in 2010, on the first floor air source and on the second floor ground source. And they found that the air source heat pumps, as we see this worldwide, require a lot more peak energy in the wintertime. And that's just because it gets cold outside. And in the summertime, they require more energy too, where the geothermal heat pumps have a much more stable energy consumption. Why? Because they're using the stable underground temperature. We can see this over and over again as in this building comparison of two identical buildings in Oklahoma, US. The air source heat pumps in the middle of the winter peak dramatically, while the geothermal heat pumps are very stable. And so we're seeing this regularly where utilities such as National Grid, which is a US-based natural gas and electric utility, they are converting from natural gas to all electric, and they're seeing a stabilization of the electric grid by doing this. It's shaving the summer electrical peak, and it's stabilizing the winter electrical peak. Another reason we do not want to roll out heat pumps all air source is because it makes the outside of our buildings unsightly, very hard to work on. It creates a situation where these buildings have a tremendous amount of susceptibility to the elements. As you can see on this rooftop in this one image where my cursor is, a hurricane left these outside air conditioning equipment just blown about the roof like so many toys scattered in a living room. These things are hard to work on when they're all outside and mounted on the outside or the top of buildings, where when they're all inside in a thermal energy network, and it makes it easier to work on. The efficiency of air source and geothermal can't reasonably be compared because the outside heat pump equipment uses so much energy because it gets cold outside in the wintertime and it gets hot outside in the summertime. So as we look at all these studies, it's evident that the real solution has to do with making thermal energy networks that will give us pipelines underground where, much like a natural gas pipeline that has an underground infrastructure, a thermal energy network pipeline, it's the same infrastructure, but delivers its energy to a heat pump rather than a furnace or a boiler, creating heating and cooling for a building versus just heating only. And in a natural gas situation, the natural gas is consumed, where in a geothermal energy network, there is no consumption, no consumptive use. It's renewable because we're using a renewable energy source here. The Cornell University campus at Ithaca, New York, is a good example of using many types of geothermal exchange. They use, in their case, the local surface water body called Lake Cayuga to cool the entire campus. And you can see that here. This is just one way to do it, but they're able to passively cool their entire campus by sinking all of the heat from the university into the surface water. If they didn't have surface water, we would be sinking it into the earth, which is relatively cool. They are currently drilling deep wells to provide up to, they're hoping for up to 100 Celsius energy from the ground, maybe even steam energy, which may create some of their electricity. They're in the process of doing this now. So they have an excellent opportunity for an unlimited amount of heat to provide the heating for the campus. If they didn't do it with deep thermal energy, such as you see here, they could also extract heat from the low temperature heat that is just barely underneath the campus. They have, however, chosen to go deep and get some more intense energy. As you look at some of these, this is the Cornell campus in New York City. They are using shallow, median temperature thermal energy to provide heat in the summer, in the winter, and cooling in the summer through a set of heat pumps down in this mechanical room that exchange heat with the shallow earth, as you can see right outside. And that thermal energy exchange takes place under this lawn just outside of the Cornell Bloomberg campus in New York City. and runs that energy through these pipes. Another example of that in the US is the Empire State Plaza, which is a pretty big state capitol. You can see these 5 towers here and several buildings around it. They provide an office environment for 14,000 New York State employees. They have for very long, since the 1960s and 70s, been combusting heat through these combustion boilers. However, recently they decided to electrify this campus and have taken this campus from an all combustion heat campus to putting in now electric heat pumps to provide heating and cooling. They now exchange and have been for some time exchanging heat with the surface water, which is called the Hudson River, to sink and source their heat for summer and winter. So as we look at the opportunities to take our communities from heating with combustion heating, we are starting to see that we can use geothermal wells, surface water, drinking water, wastewater, all these types of infrastructure sources to tie into pipelines that run through our cities and provide heating and cooling for civic buildings, office, retail, low density and high density exchange. As we're doing this in the US and beyond, we're replacing or upgrading old natural gas pipelines. Instead of putting in new natural gas pipelines, the US and many people throughout the world, many communities are upgrading to thermal energy networks, and they are replacing existing natural gas pipelines with thermal energy microdistricts. As you can see here, this case, they're taking just one street at a time in Massachusetts, and they're putting in thermal energy microdistricts and slowly reducing their dependence on combustion heating. We have found through the US Department of Energy Geothermal Technologies Office study, they call the GeoVision study, that geothermal work creates many more jobs than wind or solar. And as we're putting in these thermal energy networks, we are able to use the existing right-of-way to provide a model that provides long-lasting clean energy employment for thousands and thousands of workers currently working in the fossil fuel industry. These thermal microdistrict systems are installed, as we said, alongside city water, wastewater, electrical, and other infrastructure installations. As we're doing this, we're changing the laws to make electric and natural gas utilities thermal energy utilities. It's very important that we convert utilities from selling, they're right now selling something that is consumed, either electricity or gas. We've had to change the laws at the state and federal level to make it, right now, many utilities can't sell renewable energy because they're not selling a commodity. Thermal energy has not in the past been considered a commodity, renewable energy. Now we are changing the laws where they can sell something that is not consumed, thermal energy. And that's exactly what we're doing as we see the utilities starting to replace natural gas pipelines, which, by the way, to give you an idea, there are 69 million connections for natural gas in the United States, comprising more than 2.2 million miles of pipelines. If we could put those kind of pipelines in the United States, it's easy to see how these new pipelines, which conduct thermal renewable thermal energy can be put in. And as you see these pipelines going in, these 442-inch lines go to the new World Trade Center, and they tap into the Hudson River running right alongside New York City. And it looks just like this, one street at a time. We upgrade the pipelines and provide these thermal energy networks. And then the homes, instead of using furnaces and boilers, they switch to heat pumps and electric appliances, including the stoves. They go from stoves and ovens go from natural gas to electric stoves and ovens. Part of this, and we work a lot in New York City, is what we call the, rather than saying what we call it, it is a thermal energy grid. And you can see these big buildings being tied in. And as you look at this, and I'll blow this up real quick. Actually, I have a better view of this later. So rather than do this, you can see these different, this is tying in with the subway here, is wastewater here, vertical boreholes here. And we're tying these into the buildings and providing heat pump equipment to these buildings throughout the city. We have to convert 1 million buildings in New York City alone from combustion heating to heat pumps. When we look at this, there are studies that were done in Massachusetts that show that our high-density mixed-use buildings are about equally divided throughout the whole city between heating and cooling needs. So when we do that, we end up being able to share a tremendous amount of heating using these thermal energy networks and tying in this wonderful heat source and heat sink into our cities. So what this looks like in practicum is we take existing, and these are some of the projects that our engineering divisions work on. They take college campuses, residential apartment buildings, and campuses. And this is an example of one of them in downtown Manhattan, New York City. This is a 6-block community called Penn South. And there are 15 22-story apartment buildings that all need to be tied together to provide renewable energy resources using thermal energy networks. Right now, they use combustion heating and a central energy plant chiller system to provide the cooling and heating to that campus. Another example is the Amalgamated housing cooperative in the Bronx, New York City, US. And they have these apartment buildings, all these single family homes, these schools, these office buildings, and they need to do the same thing. So what we're able to do is design buildings that, instead of using radiators and high energy steam from combustion boilers, they use heat pumps. And instead of using cooling towers and boilers as a source and sink for those heat pumps, we use a thermal energy network, and we're able to tie that community into a thermal energy network. And when you look at a thermal energy network, what happens when you start to look at all of the heating and cooling needs in a community, you end up looking at, as you see in this graph at the top, a heat recovery potential approaching 70 or 80% of the energy that can be shared. And what that does is, in a coefficient of performance rating, is that takes, if you're taking heating equipment, heat pump equipment, and cooling equipment, and you're putting them into the same energy network, you end up taking equipment that's rated at a 3 or 4 coefficient of performance. And when those two pieces of equipment are sharing energy one with another, their coefficient of performance goes up to 9 or 10, meaning 900 100 to 1,000% efficient because they're sharing energy one with another. So that's easy to understand when you consider that normally in a building, all of the heat producing appliances, whether it's bathing, cooking, blow dryers, computer equipment, is all being taken into the air conditioning equipment and normally rejected outside. All that heat can be put into hot water systems, pools, and it can go beyond that when you look at a resort or a campus type application. That can go to cooking equipment, laundry equipment, kitchen equipment, common area equipment. And as you chase the BTUs around a building, you see that the BTUs begin to be reshared between heating and cooling appliances. So that's what these images are all about, showing that potential, as in Albany, New York here, a potential for energy sharing most of the year. So when we apply this in practicum, we end up with remarkable opportunities to share equipment and to share energy in large campuses. So this is kind of an example from this amalgamated housing complex in New York City. Not only can we share energy between all these buildings here, as in this hydronic drawing here, we started considering, what about the DeWitt? There were several schools adjacent to this, the DeWitt High School, the Bronx School of Science, Lehman College, Discovery High School. They can all become part of a larger energy network. And it really becomes something that the sky is, as far as we can imagine, is how far we can go with this, especially with all of the data centers that are being added to our society because of our intense data needs for cloud storage. These data centers are highly cooling dominant and provide a tremendous amount of energy that can be used for a number of things in industry, not the least of which is providing heating and hot water for our communities. These data centers normally use a tremendous amount of energy and fresh water through cooling towers that could be pumped instead to heat off-takers, such as greenhouses to grow fresh fruit and produce in the middle of the winter time, where in places where maybe that couldn't happen before, or other manufacturing opportunities. So as we consider all of the data center opportunities, all of the city energy sharing opportunities with infrastructure and wastewater, we begin to see that the opportunities for sharing energy are limitless. We just have to, as long as we're upgrading our infrastructure, look at this. This is a study, just a reference to a study that was done in the United Kingdom, showing that just surface water exchange with rivers and surface water bodies would amount to 6 gigawatts of energy transfer, enough to heat well over 7 million homes, heat and cool well over 7 million homes. So that says nothing about what Ritesh was starting to talk about earlier, recovering wastewater energy coming out of our buildings and extracting heat from that and rejecting heat from that. So as we consider all of these, we see that there are incomprehensible numbers of opportunities to share energy throughout our communities. And that really finishes up my presentation for today. And I just really want to thank you and take any questions for the next few minutes that you may have for me.
Yes. Thank you, Jay. We have, I think, um, 5 participants as of now, and we'd like anyone who has a question, please put them forth in the chat window so Jay can take it up for you guys. So let's see.
So just thank you for your nice presentation.
You're welcome.
And it is always nice to hear you, and I'm hearing you for the first time in the live, there are 2, 3 questions which are coming in my mind when we think of a building, the practical problems, or so how do we decide which type of system works, whether it's an open loop system or a closed loop system, and then because if we can if you can just answer this,
Yep, I will. So an open
So
loop
I just want to
versus,
add a few more things, the problems, here. So if we go to see a project, and if we get if suppose it's a hotel or an airport coming up, because a lot of airports in India are coming up now,
good,
and there are the amount of airports which are coming up is going to increase many folds, because not only mega cities but also in town to cities or other they are going to come up. So if we can incorporate this right from the very beginning, number one. And second, if we have water aquifers giving temperatures of about 22 degrees to 28 degrees temperature, and a perennial source of waters, I'm talking about cooling now, and then I'll be talking about heating also, maybe in my next question will be on heating. But first, maybe you can explain this, and then how can we just start making some very interesting projects, and people are interested to make buildings green. But if we can just give them right consultancy, or maybe open a curriculum for them, for the students, as you said, that it can create a lot of jobs, but jobs will come only if they have some knowledge,
yes,
but I think in India the problem is we have very few experts on ground source heat pumps, and then they are not very conversant or fluent. Only very one or two, or maybe they're doing some very good job. Otherwise, they are just not able to deliver good results. Maybe due to drilling, maybe due to grouting, maybe the heat exchanger which they are putting up is not good, or maybe we are not getting climate masters, or this furnace uh, are not designed properly, or there is some problem is happening here, and that is why we are not able to implement it here properly. So I would just like to ask you first regarding this heating, this cooling, how we can just start with the in India, as it is a budding market, and we have a lot of not only buildings coming up, townships coming up in 2 tier cities, but the airports, the hospitals, and a lot of infrastructure is going to come up in, I think, by 2020, and maybe by 2050. We may increase our air conditioning facilities from, say, what is we are having now, to maybe around 10 times or maybe 100 times more, because
very
cooling
good.
is a problem in India. A lot of people die because of heat waves and all. And now with the growing economy, more air conditioning will come up, more problems, more electricity bills, and then they are not able to meet it, and then it gets most of your finances from your house budgets. But if government can take up this networking, the thermal networking, what you are saying, and then we can just bid in very strongly with the government, Ministry of New and Renewable Energy, and try to figure out how we can just make it a policy matter, as you have done in your states. Because here we have to change some bylaws in groundwater extraction. Then someone will come up, yeah, you are extracting groundwater. We are not extracting groundwater. There are a lot of permissions. So groundwater drilling and geothermal installations for heat pumps has to be done categorically differently, and that has to become a policy matter. And then how do we proceed to the government? Maybe in coming days we take up this matter with Ministry of New and Renewable Energy, and then maybe we may need you and your documents in helping framing the right ground source heat pump policy for the Indian subcontinent. And then for cooling, yes, we would like to have an answer. Then I will ask another question that is regarding heating in the Himalayas. So first, from Indo-Gangetic Plain to the peninsular part, where we are looking for cooling the systems effectively, and that is what maybe you can just answer that.
Thank you. Those were some very thought-provoking and excellent questions, Ritesh.
Thank you.
I want to apologize if we're not able to get to it all, because I have to leave at 1:30 for another meeting, but we still have 12 minutes and I'm going to address this. You talked about policy, and that is, this really, if you don't, just understanding the US, it seems that California and New York seem to be the two US states that where policy is at the cutting edge. And we have, for the last 10 years, worked closely with New York in developing policies, not only for requirements and that make heat pumps an absolute necessity for decarbonizing buildings, but also different policies that there is a program in New York called the Community Heat Pump Program. And it is one of the programs we're involved in, where consumers that own buildings are paid a goodly amount of funding to consider going with heat pump technologies. So we will come in and we will explain this to consumers that want to upgrade to heat pumps, and then the New York State government will give them an opportunity to put in an application for their idea. Then the New York State government will fund it if it's a good idea, and help take the burden of implementation off of these building owners. So these types of programs start at the federal level, where there's a federal tax credit for heat pump implementation. Then there is a state incentive for implementation. And then the state also empowers the electric utility to pay a tremendous amount of money to people, to homeowners and building owners, to upgrade to heat pumps. For example, one of the projects we're working on, and I had an image of it, right? I'll just go back to it so it's referenceable. This community here is hoping to get about $88 million in utility subsidies to upgrade to geothermal heat pumps. And there are 2,500 families that live in this community here. So those types of things, it isn't just the incentives that the government is giving. There is also a grading that the government does in New York City for these buildings. They come to these buildings, and the New York City government comes in, and they come to every building in New York City. They come in and give the building an energy grade, A through D, A being good, D being a fail. And if they are emitting carbon, in other words, greenhouse gas emissions, the more they're emitting, the worse their grade is. And so as we look through these, the buildings actually have to display these placards that give their energy grade, and they have 10 years, roughly, I'm just throwing out a number, 5 or 10 years to start working on that, or else the city government will fine them, and it can be millions of dollars a year for emissions that are causing damage to the health and safety of the world. And so not only do they have incentives, but they also have, we call it, there's teeth teeth in the law, which teeth in the US or in English means there's a danger of not acting, right? So they have to act or they get fined. And so that's part of it. Not only do they provide the incentives, but they provide a fine or a bad result if they don't act on this. So many of the folks in the US act out of the necessity to keep from having a financial burden placed on them. So that's what it takes, both of those. I've noticed during my 35 years in the industry, it takes both incentives and a repercussion if you don't act to get people to act on these buildings. And so what we can do, and probably anybody else who's at our level in the US, we can help, and this is what we do in our advocacy work, we can help local government officials by showing them in India what is working in the US to help people move toward conversion to heat pump technologies. And you asked specifically, Ritesh, about how do we determine whether it is better to do a surface water or groundwater exchange, or whether it's better to do closed loop or any other. That's usually done through an engineering study, as you're probably familiar with. It's good to share this with everybody. When a building or a community comes to an engineering firm and says, we want to have a geothermal energy network solution, what is the best way to do that? The first thing that is done is what's called a scoping study. And the scoping study just gives us an overview of all of the, and this is kind of what this is meant to talk about. A scoping study gives us an idea of what, and this is an image of a study here, and here's an image of a study here. And we kind of determine what might work best for that area. And we put a little bit of time into it, maybe a couple hundred hours, and provide a report. Then after the scoping study is done and we decide which one we want to do, and you can kind of see it here, this has a recommended upgrade for one of the projects. It says it right here. This is recommended. These other two were suggested. Then we go into a feasibility study once we know which way we want to do it. And the feasibility study actually gives the owner of the property, whoever commissioned the study, whether it's government or the owner, an idea of how much it will cost to do it. And then what the engineering hurdles are to do it. And then we will do that. If they choose to do that, we actually go to construction drawings. We start developing the construction drawings. And by the time we're done with all of that, we end up with actual construction drawings to start installing these energy networks into buildings and tying them in such a way where they end up with the energy network that will give them the final answer for their facility. And it's beautiful to have these types of images here, because you can kind of see at a glance all of the possibilities that might be available to a community, whether it's a residential community or an apartment community or a city center or factories or wastewater treatment or rapid transit, even the city zoo, you know, or the Tethys Fossil Museum can be part of that. Maybe that's where we end up starting it there, yeah, and share it with other folks from there. But I know that I haven't been able to nearly answer all this, and I want to say one more thing before I turn the time back over to you. We have educational modules that are used by universities and colleges in the US that provide technical and engineering guidance for designing these systems, and we've developed them for the university system. And it's what you've heard today is about an hour and a half, but there are countless hours of indoctrination and training, whether it's a tradesman that does pipe fitting or welding, or it's an engineer or an architect that designs these systems. We go through several courses of education to get the local engineers, architects, and trades up to speed to do these systems. So with 2 minutes left, I want to turn the time back over to you, Ritesh and Oshin, for any follow-up comments. And we can follow up on questions by email and so forth.
For sure, Jay. I would just like to thank you, Jay, for educating us on clean heating and cooling heating and geothermal heat pumps and pipelines, compressors, and how these frameworks work in the US. It was really enlightening to watch. So I would like to ask Dr. Ritesh if he has anything to add to this, and we can maybe perhaps conclude the session with that.
Yeah, I think yeah, it was very enlightening, and I think when we put it on the YouTube, and lot of students and a lot of policymakers, and we will just try to circulate it to the politicians also and the administration also, who are framing policies on geothermal, and to say that they have to look beyond sun, they have to look beyond wind, and then everything is just beneath them. Wherever they are, they can find energy either for heating or cooling, and then the mechanism has to be done. Some institutes have to be built where we educate them, and then we may require your help in that, or maybe some good pilot projects which come up, then we can work on that, because we may go in geology and drilling, but definitely when it comes for designing of heat pumps, we are maybe now in a very infancy stage, and
Thank you.
yeah, but definitely we'll love to work with you and learn from you a lot in near future also.
I am looking forward to it. I cannot wait to meet you in person, and we are going to, this is the beginning of a wonderful relationship. Thank you so much for inviting me.
Thank you, Jay. Thank you very much.
Thank you.
Thank you very much. We are just.
Thank you all who were able to attend this lecture, and we thank Dr. Hariraj Dandi for sponsoring these webinars for 2022. We greatly appreciate his generosity and giving us the strength to support the cause of promoting and preserving the fossil wealth of Himalayas and having these webinars on geothermal systems. So thank you.
Thank you.
Thank you, Jay.
We'll see you again. Bye.
Also, for further updates on lectures and webinars, follow us on our Instagram page, Tethys Fossil Museum, so everyone can stay in the loop. Yeah.
I'm going to get on that. I am going to get on my Instagram. Thank you.
Great.
Thank
Bye.
you. Thank you. Thank you. Bye-bye. Thank you very much. So we ended now. Thank you very much for attending. So we are ending it now.